Okay, I guess I can start us off. So today we're going to be talking about the Fibonacci sequence and the golden ratio, which I think is a super cool topic because you can see it all around you. So you guys are in for a treat. Reese, you can.
So does anyone know what the Fibonacci sequence is?
Has anyone heard of it before?
Yeah, someone put the beginning of it in the chat. So it's the sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So what do you think the pattern is in the sequence? Yeah, for each term you add the 2 previous terms to get the next term, and you just keep doing that.
So now that you know the pattern, let's look at the next couple of terms in the sequence. I think somebody already put in a lot of numbers in the sequence. So what would be, list out like the next 5 terms or just the next couple of terms. Yeah. So to get the next term, you just add the previous 2 terms. So 21 plus 34 is 55. And then 55 plus 34 is 89. And then 89 plus 55 is 144. And then you keep going on and on and on. And this makes for a very interesting sequence. And we're going to explore some of the properties about it that you might not have heard before.
So something that's related to the Fibonacci sequence is the golden ratio, where A over B is approximately equal to A plus B over A, and A has to be bigger than B. And any pair of numbers that fit this are known to have a golden ratio.
So let's look at let's fill out this little chart and see if like the numbers here, like how they show the golden ratio. So first, what is A divided by B? And you can probably use a calculator if you'd like. Yes, that's correct. So A divided by B would be 3.236 divided by 2. And so that's approximately 1.618. So next, what is A plus B divided by A? So the sum of both of the numbers divided by the larger number. Yeah, so that would also be 1.618. So would that then be the golden, would these two numbers be considered in a golden ratio? Yes, they would be considered in a golden ratio because they satisfy both of these requirements. So the big number divided by the small number and the sum of the numbers divided by the big number both have the same ratio. So what about these numbers? 22.64654 and B equals 14. So would these what would be the value of A divided by B, and what would be the value of A plus B divided by A? Yeah, A divided by B for this example, it also equals 1.618. And A plus B divided by A, that would be 22.654 plus 14 divided by 22.654. So that also approximately equals 1.618. So these numbers would also be in a golden ratio. So this is another example of a pair of numbers that are in a golden ratio. So finally, our last example over here, oops, I just showed you the answer on accident, would be 10.225 and 6.32. So for this one, you can just jump to the end. So would these numbers be a golden ratio? Yes, these numbers also have, they approximate the golden ratio of 5. So these would have a golden ratio in it. Okay, so you guys probably noticed that for all the ones that have a golden ratio, it's like this number, right? 1.618. So
that introduces the golden ratio value. Every number that has a golden ratio will equal approximately 1.618. And there's a Greek letter that's assigned to this number called phi, which is used to express this value, and it's irrational. So there's a way to say it in exact terms, which is 1 plus the square root of 5 over 2, which will equal 1.61803, and it just goes on forever. And it's similar to how pi equals 3.14.
another way to express this irrational number is to write this infinite fraction. This infinite fraction also equals this value of phi. Although I say it's 5, but I feel like I'm pronouncing it wrong because I pronounce most things wrong. So it's probably phi. Okay, so this, when the golden ratio is applied as like a growth factor, then you get this very interesting spiral. Oh, if some of you guys are in 7th grade and you're in this class, it's fine. it's okay. You can just enjoy like the 8th grade experience. So yes, the golden spiral would be just the golden ratio as a growth factor.
So now we're going to connect the golden ratio and the Fibonacci sequence. So remember that the golden ratio, A divided by B, will always equal approximately 1.618. So now on the next slide, we'll divide all the numbers in the Fibonacci sequence with its previous number. So 13 divided by 8, and so on.
So over here on the first row, we have all the numbers in the Fibonacci, or the first few numbers in the Fibonacci sequence. On the bottom, we have like them divided by each other. So for the first one over here, you can see we've already written the first few. So like 1 divided by 1 is just 1, right? So that's what we've written there. And then 2 divided by 1 is just 2, which is what we've written there. So what is 3 divided by 2? Yes, 3 divided by 2 is 1.5 in decimal form. So Next, what would be 5 divided by 3? Yes, roughly 1.67. What is 8 divided by 5? 1.6, that's correct. And 13 divided by 8? Yep, it would be 1.625. And now you might need to start using a calculator if you haven't already. So what's 21 divided by 13? Yes, it would be around 1.615. Obviously, it goes on and on, but we're just going to round. So what is 34 divided by 21? Yeah, it's 1.619. 55 divided by 34? It's around 1.618. So you guys might be starting to notice a pattern. So the next one, 89 divided by 55, would also be like it's not exactly 1.618, but if you round like to the thousandths, then it would be around 1.618. And so for the rest of these, they all like start to get closer and closer. So what's the pattern here? So like I'm sure you guys noticed something interesting going on. Yeah, exactly. They're all like getting closer and closer and closer to the golden ratio. And in fact, what they're sort of doing is they're sort of like they're sort of jumping around the golden ratio. So like they're jumping a little over the ratio, a little under the ratio, a little over the ratio, a little under the ratio, and they're just like zigzagging closer and closer and closer to the actual value of the golden ratio. So what this sort of means is that in the Fibonacci sequence, as you like proceed like down the sequence, the ratio of the different numbers will approach the golden ratio, which is very interesting. It like connects the golden ratio to the Fibonacci sequence.
Okay, so now we're going to do an activity. So Amy's going to put a link to a Google Slides in the chat. And so you just have to go there. And so as you can see on the Google Slides, there are like squares, and each square has a length and width of a number in the Fibonacci sequence. So all you have to do is arrange them in a way that will make it a rectangle.
Yep, and make sure that you make a copy of the slide. So don't just directly start dragging everything around. Make a copy of the slide and then put your name on it so that people know it's yours. If you guys don't know how to make a copy of the slide, I will make a copy for you. Okay, spread out. So yeah, basically you're trying to arrange to make a rectangle.
Yeah.
And do keep in mind that there's actually more than one way to make a rectangle. So there are actually many different arrangements of this that can. Oh, wait, you're not making a copy of the slides. You're just making a copy of the first slide in the whole slideshow. It's like once you're on it, you can just go to one of the blank ones and just start messing around. So for all you people on the first slide, you can just go to one of the slides that haven't been occupied. I'll just add more blank ones for you. Just go to one of the slides that hasn't been occupied and you can start messing around on there. You don't have to make a copy of the slideshow, just of like one of the slides, which I already did for you. Wow, it looks like some people have gotten it.
Could someone add a slide for me?
Yes, I will. I think slides 8 through 10 are blank. So you can take those. Otherwise, I can also add a slide at the end.
So we were just supposed to make like a rectangle out of the ones that you've given us, right?
Yeah,
Okay.
I see some people have made very nice rectangles. Okay, so if you just came in, I'll put so we are going on this slideshow and pick like a slide that hasn't been like taken by someone. So I think slide 9 is available. So go on that slideshow and try to drag the squares together to make a rectangle. So today we are learning about the Fibonacci sequence and the golden spiral and the golden ratio. So that's why we're doing this activity. I'm putting stars on people's slides that have made a rectangle. Ooh, very nice. Yay. Oh, if it's not gonna let you edit it, I guess that's okay. you can just look at other people's slides and look at how they've made their rectangles, because there's many ways to make a rectangle. It is kind of difficult to make it on a phone. I know some people were having trouble with like accidentally changing the sizes of the squares and stuff. I'm just gonna give it a sigh. That's close enough. Okay, so if you're done, you can go look at other people's slides and look at how they made their rectangles, because you can make it in different ways. However, I do want you to notice that, yeah, it is hard to move the little squares on a tablet or a phone. So notice how like other people made like rectangles using different arrangements of the squares, but in all of the squares, there are always like two squares bordering a bigger square, and the two smaller squares that are bordering the bigger square are the two previous Fibonacci numbers, because together, if you put those numbers together, then they add up to equal the side length of the bigger square. Yeah. Okay. So some people notice, I guess it could say like some people's rectangles, like Schloke's rectangle, all of the squares are moving down. The smallest squares are moving towards like the bottom right of the rectangle, whereas other squares like, or other rectangles like Henry's, they're moving towards sort of like the center of the rectangle. And that's, you're going to see, like if you arrange it sort of like how Henry did, you can actually fit the golden spiral inside of it. So I will take a copy of that, hopefully. So you can actually arrange it so that the golden spiral fits inside. Okay, let's head back to the slides now. Yeah, so I just showed you guys how, like, if you arrange it in this way, where each square sort of rotates, is placed like in a like rotating manner, where it's like on a different side of the square each time, you can fit the golden spiral right inside of it. Yes, you can calculate the length of it. You can approximate it by looking at the diagonals of the squares, kind of. Reese, you want to talk about this?
Oh yeah, okay. So does anyone know where Fibonacci numbers are seen in the real world? Yeah, someone said the next example. Yeah, Fibonacci numbers are seen in flowers.
Any other ideas?
So yeah, someone already said this. If you didn't know this, if you go outside and count the petals on flowers, most likely the amount of petals will be one of the Fibonacci numbers. So you have some examples here. There's more examples, but this one just goes up to 13. And we also have a math problem that relates to flowers. Your friend Peter Parker gives you a basket filled with flowers. In the basket, there are 6 different types of flowers. For each type, the amount of petals are a unique Fibonacci number from 2 to 21. The amount of flowers of each kind equals the amount of petals, so there are 2 flowers with 2 petals, 3 flowers with 3 petals, and so on. What is the probability that you randomly pick a flower that has less than 8 petals?
So take a couple minutes and work this problem out. And once you get the answer, type it in the chat. Looks like we have one answer. It does need to be simplified though. We have 2 answers. Three answers.
Yeah, so people are getting the right answer. Basically, what you would do is first you find the total number of flowers in the basket. And so that would be 2 plus 3 plus 5 plus 8 plus 13 plus 21, which is 52. And then you find out how many flowers in that basket have less than 8 petals, which will be the Fibonacci numbers from 2 to 5, because it says less than 8. So that would be 2 plus 3 plus 5, which is 10. So it would be 10 over 52, which will simplify to 5 over 26.
Yeah, I figured you guys just made a silly mistake. So good job, everyone. Okay. No, I don't think anybody talked about this, but you can actually find the Fibonacci numbers on the piano case, does anyone play piano? Or does anyone play any instrument at all? Okay, it looks like we have some people who play piano. Okay, so you guys probably know a little bit about music then. So on piano keys, you can actually find the Fibonacci numbers. So there's like on a piano, like let's just look at like one octave. So like in one octave, like from C to C, we can find the numbers 2 and 3. Where write in the chat where you think you can find the numbers 2 and 3 in like this arrangement of piano keys. Think about the number of and types of keys. If you need a hint, here's the two black keys. And then the 3 would come from the other 3 black keys. So that could be one way you would find these first few Fibonacci numbers on the pianos, because there are groups of 2 black keys and groups of 3 black keys in an octave. So on that note, where would the 5 come from? Yeah, 5 would be the total number of black keys, because there are 2 black keys over here, 3 black keys over here, so there'd be 5 black keys in total. So where would the 8 come from? Yeah, it's the total number of white keys. So total number of white keys in an octave. And oops, where would the 13 come from? Yeah, they're the total number of white keys and black keys combined. So see, the Fibonacci numbers are everywhere. You guys, until like now, you probably never noticed that. But I guess now every time you look at a piano, you should think there are Fibonacci numbers on it. Okay, so let's do a problem with that. So baby Kate is randomly banging on a piano in a attempt to play Twinkle Twinkle Little Star. So the piano has 1 octave, so there are 13 notes. And if baby Kate gets a note right, then her mom will give her 2 cookies. But if she gets a note wrong, her mom will take 1 cookie away. So if Twinkle Twinkle Little Star has 42 notes, what's the expected value of the number of cookies Kate will get? And if you haven't learned expected value yet, if you haven't learned expected value yet, then it's basically like literally like the expected value of cookies. So you use the probability of an event happening and you multiply it by the outcome, and then you sum all those together. If you don't understand that, I'll walk it through. So oh, for 13, we mean like including the black keys. Do you guys want more time, or do you want me to just explain? Okay, I have a couple of answers. Okay, more time. I'll give you more time. We have, okay, I will give you a little hint. The answer is ridiculous. Because it's like expected value. Like expected value is kind of, I don't think anyone has gotten close yet. Okay, do you still want more time? Okay, Savi still needs more time. I'll give like another minute or two. Yeah, I don't think we've actually taught expected value fully yet. So you guys will learn something new in this problem. Okay, I'm gonna go over it now. So let's, for now, it says like twinkle, twinkle, little stars, 42 notes. But for now, let's ignore the fact that there's 42 notes. Let's just think about her, like that kid getting just one note correct, like just the first note. So what's the probability that they get the first note correct? Yeah. So there is a 1/13 chance that they will get a note correct. And so in the event that they get the note correct, how many cookies will they get? 2, right? They'll get 2 cookies. So when you're calculating expected value, you multiply the probability of them getting something by the thing that they're getting. So there's a 1/13 chance that they'll get 2 cookies. And then you multiply that by 2 cookies because there is a 1 in 13 chance of them getting 2 cookies. So that means, however, we also need to take into consideration the fact that they might not get the note correct. So what's the chance that they get the note wrong? Yeah, that's 12/13. And then how many cookies will they get if they get the note wrong? Yeah, they will get -1 cookies, unfortunately. So this is the expected value for the number of cookies you will get for the first note, which is actually a negative number. So this is -10/13, right? So this is just, and this is the thing is, so this is just for one note. How many notes are there in total? Yeah, so she's playing 42 notes. So how many cookies can she expect to get? Oops. -10/13 cookies per note times 42 notes. Well, unfortunately, baby Kate is going to owe her mom 32 cookies-ish. So remember, this is expected value. So things can be a little bit wonky. Like there might be negative numbers or fractional things that can't be fractions. But this is just saying that she would expect to lose 32 cookies. So if she had like, if baby Kate had like a bunch of like cookies in her cookie stash and Kate's mom had to keep taking cookies away, she'll have to give her mom 32 cookies from her cookie stash. So that's what this means. So this is expected value. So unfortunately, she will have to lose 32 cookies. But look, she tried her best.
Okay, so here's somewhere that you probably would have never thought that you would see Fibonacci numbers. But if you measure like your hand from each joint, then the ratio of here to here will be 2 to 3. The ratio of here to here will be 2 to 5. And the ratio of here to here will be 5 to 8. And if you're like me and your hand is exactly 18 centimeters, then this will be exactly 2 centimeters, 3 centimeters, 5 centimeters, and 8 centimeters. But obviously, everyone's hand is not the same. So if you want to find the exact length of each, then you would use the equation right there. So 8x plus 5x plus 3x plus 2x will equal the length of your hand.
And obviously people's hands are slightly different. So it might not be like exact, but it's pretty close to like the ratio here. It's very close.
So our math problem, Kendall Jenner has quit her job as a supermodel and wants to become a hand model instead. On her application, the modeling agency asked her for the length of her middle finger's proximal phalanx. If Kendall's entire hand is 17 centimeters, what is the length of her middle finger's proximal phalanx? And so if you don't know what that is, it's like right here. It's on your middle finger, it's the third one going down. Yeah.
It's this part. It's like the third section on your middle finger. It's like this. I'll go back to the ratio slide. So so the proximal thingy, that would be this section here. Yes, they are intertwined. And her whole hand is 17 centimeters.
Yeah, so we got one answer.
Yes.
Yeah, so you guys are getting the right answer. So basically how you would do this is, since it's a ratio of 8 to 5 to 3 to 2, 8x plus 5x plus 3x plus 2x equals 17, which is the length of her entire hand. And after combining like terms, you'll get 18x equals 17. And divide 18 on both sides and get 17 over 18 is x. So then you go back to the original equation and plug that into 5x and get 4.72 centimeters.
Good job. Okay, so previously we asked where you could see Fibonacci numbers in real life. So now, where have you guys maybe seen the golden spiral in real life? Yes, an ear's good one. Yes, fossil. That's a really good one. Lollipops, I guess. Yes, shells are a pretty good one. Earlier, I think for the Fibonacci numbers one, somebody said wave, and I think that's a good one because like when waves are breaking, they often have that curl at the end. Rope, yeah. There is some overlap too. So like plants and like flowers and ferns, I think somebody said ferns earlier, they would also display that. Yes, shells. Yeah, so earlier, a lot of you guys were talking about flowers, and because the Fibonacci sequence and the golden ratio is sort of like intertwined with each other, you can often find the golden spiral in plants and stuff. Would gravity be an example? Like what about gravity? Like, do you mean like the magnet? Potentially. So in plants, the way to find the golden spiral is to look in like sunflowers and stuff, because in the seeds, like the way the seeds are arranged are sort of in the Fibonacci sequence. So because of that, you can often find the golden spiral in how they're arranged. Also, like same goes for like the arrangements of leaves. Sometimes they are in a spiral form for similar reasons as like the seeds are arranged. So ears, yes, and ear is a good one. So let's do a thing with sunflowers. So let's say a forest has 27 sunflowers. Every year, each sunflower has 3 seeds that fall and turn into a new sunflower. So how many sunflowers would be in the field after 3 years? Can the Coriolis effect count in a way? If we're talking about like hurricanes, maybe, because Coriolis effect causes hurricanes to spin. So yeah, I guess so. Hair, potentially hair, if your hair is curly. My hair is not very curly, as you can see, so. I think something that nobody said was galaxies. Some galaxies, spiral galaxies, you may be able to find something that resembles the golden ratio in it. Okay, it looks like we have a few answers. So the forest starts with like 27 sunflowers, right? So each year, each sunflower has 3 seeds, right? So I'm just gonna represent it with this. So the 3 seeds, they turn into a new sunflower, but you have to sort of include the original sunflower in your calculation. So it'd be 27 times 4, and then times 4 for the second year. So the first 4 would be the first year, second 4 would be the second year, and then the third 4 would be the third year, because you have to include the original sunflowers that grew up the previous year. So after 3 years, there would be 27 times 4 to the third sunflowers, which would be 1,728 sunflowers. So I think some of you guys might have done 27 times 3 times 3 times 3, but you have to include the original one. So I originally forgot to include the original sunflower in the calculation. Does anyone have sunflowers in their garden? Interestingly, last year I had 1 sunflower, and this year I have 3 sunflowers because some of the seeds are growing up. Unfortunately, one of the 3 sunflowers died. I'm not sure why, but it just kind of fell and then it died. Ooh, are they like the mammoth sunflowers? Like, are they the ones that have really big flowers, or are they the ones that grow really tall? in the past, the sunflowers I've had have grown like very big, like middle, like the petals are teeny tiny, but they have so many seeds. It's insane.
So I heard a lot of people saying ears. That is a place where you can see the golden spiral, and also seashells, and it's not on here, but snail shells.
Yes, elephants.
So Dumbo is late to his performance at the circus because there's traffic. So he's considering getting out of his vehicle and walking. Considering the following information, will it be better for Dumbo to walk or stay in his vehicle? And so the first thing is the cars are going an average speed of 27 miles per hour, and they have 20 miles till arriving at the circus. But Dumbo's fastest walking speed is 25 miles per hour, and if he walks, he can take a shortcut that is only 19 miles away from the circus. So, should Dumbo stay in his vehicle or should he get out and walk? Yeah, so people are saying car. So, let's see how long it will take the car to get there. So if the car is going 27 miles per hour and they have 20 miles left, then what you do is divide 20 miles per hour by 27, and that would get you 0.74 hours till he gets there. While Dumbo, if he walks, he would have 19 miles and divide that by 25, which will get 0.76. So you guys are right. He should stay in his car and be patient.
Something else, some other places where you might be able to find the golden ratio. I don't think anyone said this either, but you can actually find it in like art and in paintings and stuff. So I think the Mona Lisa is the most famous for this, because it kind of like, if you start it at her hand, it very nicely goes into her face. And then in other paintings as well, the layout does kind of match the golden ratio, the golden spiral. I think another place that sort of relates to that is architecture, because you can sort of find the golden ratio in like Greek architecture and the way they designed their buildings, which is very interesting. So let's say that Vincent van Gogh, a long time ago, wanted to paint a self-portrait, and he wants the canvas to be a golden rectangle, which is basically just, it's just when the length divided by the width is the golden ratio, so that he looks like good in it, right? So if he wants the width of the canvas to be 3 feet, which is, in other words, like the height of the canvas to be 3 feet, what would be like the length of the canvas? Some painters did. Some painters actually did like do some. I mean, I don't know if Vincent van Gogh did, but I know some painters did purposely try to make their paintings nice looking using math. Also, Van Gogh was sort of a math science dude too, so. Okay, I see a couple of answers. The answers are a little bit mixed at first, but it looks like a lot of people are saying 4.854 now. So we're solving for the length, which I'm just going to call L, and then divide by the width, which is in this case 3. And so this should roughly equal 1.618, the golden ratio. So if we multiply both sides by 3, then you would get 1.618 times 3. That would be around 4.850, 54. So yeah, that would be the answer. That would be what the width of his canvas needs to be in order for him to like make it look nice. Although honestly, you could probably use all of the different types of lengths and widths. It's just that people are sort of like drawn to like the golden ratio because they think like it makes their like pictures like look better.
So another place where you can find the golden spiral is our hands again. If you just do a fist with your hands, then it will like, then it like spirals.
You can make the golden ratio using your own hand, guys. Okay, for this next activity, it's basically, I'm gonna send another Google Slides link in the chat, and hold on. And basically, you're gonna find examples of golden spirals and put them on your slides and paste it onto the slide. And you can, for this one, you can all work on the same slide and just make a new one if the first one gets too full. And I can also try to fit the golden ratio onto the slide you guys are looking at. I'm going to make a copy of this slide just so it does, because I have a feeling it's going to get really full. And the other thing is that, here we go. So this is the golden spiral for reference, just in case you guys need to look at it. If you want to fit it onto the pictures you find, then you may. So I think for this, you can, if you find them like on the internet, I think that's fine. If you also have like your own pictures of something that you think might be cool, like if you went to the beach and found a very cool looking shell, then you can also paste it onto the, I actually have a shell to show you.
Can you explain the egg? How is an egg of the golden spiral? Oh, okay, that makes sense.
Yeah. Okay, I have a personal example. I found this very cool shell when I went to a beach in New York City, and it is very cool. It has like a spark. It's not like a colorful shell. It's kind of gray colored, but I think this is a cool example. Ooh, her tang is a nice one. I think it's just the sound that the blocked airflow makes. What is that ear? You guys should try to find some examples of Greek architecture that have the golden spiral in them. Oops, what happened? Oh, there we go. Ooh, that's an interesting plant. Oh, it's a pepper. That's a good one. A caterpillar. Yes, a galaxy. Do you have something in your room that looks like the golden spiral? That's okay. It's hard doing it on a phone. Do you have something on in your room, maybe? I don't know. I don't know if you're the type of kid who collects seashells, because I was like that type of kid who would like go around and scoop up all the seashells on the ground. I can probably find another seashell. Okay, here are a couple. Oh, okay. Thank you for your contribution. Okay, so I have some examples of spirals. This one is a broken seashell, but it has a spiral on the end. There, you can see it now. And then I have another broken seashell, but it is also a spiral seashell. And then this one is very nice, but unfortunately I only have like this chunk here. It looks like this. And then I have this single shard of what must have been a pretty big seashell, because this is just the outer edge, but I don't have the rest of it. It was just a piece I found. What is that video about? Related to what we're learning? I'm afraid it's going to be a Rickroll. It's about whales forming a Fibonacci. Oh, that's very interesting. You should put on the slides. You could like, here, I'll insert it as a video on the slides. Oh yeah, okay, it's not a rickroll. Oh yeah, that's really pretty. That is very pretty. Oh, the first slide has become interesting. Oh yeah, the stairwells, yeah, spiral staircases are a very cool example. Oh yes, rams. I forgot about that. Ram horns, like they grow out in a spiral. Each year a new like ring is added. Whales. Sonic the Hedgehog. There we go. That's nice. Okay, do you think we should move on, or should we spend a couple more minutes? Okay.
You guys can come back later and put stuff on the slide if you want. Okay, so these are mathematical applications to of the Fibonacci numbers. The first one is Pascal's triangle, and if you don't know what that is, it's basically a triangle where each number is the sum of the two numbers above it. So like, for example, where 4 is, that's 1 plus 3. Or like 5 would be 4 plus 1. And it's usually used in algebra and probability. And so if where the Fibonacci numbers are, if you diagonally add the numbers in Pascal's triangle, then you'll get the Fibonacci numbers.
I think in Pascal's triangle, you might see it used in like, in algebra, you use it for finding when you're doing the binomial theorem. And then in probability, you use it when you're doing combination calculations. So the other interesting place that the Fibonacci numbers pop up is in Pythagorean triples. So you guys probably know what the Pythagorean theorem is. It's where A, B, and C are the sides of a triangle, with C being the hypotenuse. Then A squared plus B squared equals C squared. And so integers that satisfy this theorem are called Pythagorean triples. And this is used in right triangles. So for example, 3 squared plus 4 squared equals 5 squared. These could be the side lengths of a right triangle. So 3, 4, and 5 are a Pythagorean triple. And the thing is, if you start with like 5, right, starting with 5 in the Fibonacci sequence, every other number will be the largest number of a Pythagorean triple. So that would be like 5, and then every other number. So 13, 34, 89, 233, and on and on and on. So 5 is the largest triple in the 3, 4, 5 Pythagorean triples. 13 is the largest number in the 5, 12, 13 triple. 34 is the largest number in the 16, 30, 34 triple. 89 is the largest in the 39, 80, 89. and 233 is the largest in the 105, 208, and 233 triple. So it's kind of weird how it sort of like pops up in different places like that.
So the next one is regular pentagons. For all regular pentagons, if you take the diagonal, which is shown with the red line, and the side length, then that is a golden ratio.
Also, there's also a thing that's called the golden triangle. So basically, if the triangle has side or angle measures of 36, 72, 72, this is called the like golden triangle. And this is also found in pentagons too, so they're kind of related. So the reason why it's called the golden triangle is because if you draw the bisector AD that bisects angle A, so it divides angle A into a 36 angles, then it actually ends up dividing the opposite side in a golden ratio. So CD is in a golden ratio to BD. And you also might notice that it divides the triangle into more triangles that have degree measures of 36 and 72. So this angle here is 72. And so this will be another, and so this will be another like one of those golden triangles. So you could continue doing that thing where you bisect it and so on and so forth. So like this. Okay, so it looks like we finished a little bit early. So we can go back to the slides and see how much it has changed. So the first slide is still kind of interesting. I think the worm looks cool. It does look a little bit like, I don't know, you know, that feeling. Okay. Looks like we have some other things on this slide. Then we have, ooh, okay, that's interesting. Yeah, looks very cool. If you guys find examples of like the golden ratio or golden spiral, like in your day-to-day life, you can take a picture of it and post it on the Google Classroom if you feel like inclined to do that.
Can we get 3 points for doing that?
Point? Maybe we can give you 1 point if you post something. We won't give you, how about this? If you post something that is an example of like the Fibonacci sequence or the golden ratio or something on the Google Classroom, we can give you 1 point.
So like for thing.
Yeah, just for, it's not like for each thing, because otherwise I feel like some of you will go out and take a bunch of pictures of flowers. It's not for every post, just like 1 point just for posting something. Yeah, it does get reset. That was everyone's, you know, we can give people who are a little behind another chance. But yes, we can give you 1 point if you post something, but it has to be like a picture that you took. It can't be like something that's like taken from like Google. Like you have to like go outside and like actually like look for flowers and stuff. Oh no, it's top 3. It's top 3, I think. We said top 4, that way the fourth place people would know like how close they are. So top 3 people will get prizes this week, and then top 3 people next week will also get prizes. I'm not sure what Aryan is saying. The score differences are so low though. After today, there's probably a bigger difference between the scores. It depends. There are some people that are ahead. Okay. Oh, are we going to post the results today? probably today or tomorrow. We still need to like tally them up, and and also try to post the pictures about the like golden spiral and everything before the end of today. So after, if you post something tomorrow, we might not give you a point for that. Who makes these slides? So Ruth made the slides for this one.
Yeah, but everyone else, like, we all take turns in making slides.
Yeah. So like I made the slides for the first 2 lessons this week, which were fractals and math point geometry. And then Kyung, I made the circles one. Yolanda made the Euler's formula one, and Ruth made this one.